Okay, so today we are going to talk about definite integrals and how they relate to stuff. Okay? That's basically why we did what we did. So on your quiz, you had to do area approximations, maybe with 6 rectangles, maybe with 8 rectangles, okay, and that approximated our area. Now, the more and more rectangles we make within an interval, what's going to happen with our area?
It's going to get more and more accurate.
Okay, it's going to get more accurate. So, the smaller the rectangles we get, and more of them, okay, the closer we're going to get to our actual area, okay? So what we need is a way to add up an infinite number of rectangles. Sounds impossible, right?
Oh, I'm sure it's not. You're going to show us now.
It's called the Riemann something.
You're genius. I love it.
Okay. So, it's going to involve a limit towards infinity. Okay. What we're going to do is we're going to find the equation of the sum of our number of rectangles, and we're going to take the limit as it approaches infinity. So we're going to take the number of rectangles towards infinity, and they're going to be infinitely small rectangles, and we're going to add infinitely many of them up together to get our exact area. Now you know nothing of what this means right now. Okay? We will break this apart. Do not worry. Okay. So we're going to talk about this a little bit, and then I'm going to actually tell you what f of x sub k means. All right? So this is the process that we're going to do by taking this limit, okay? First of all right, and don't feel like you need to write everything down on this slide. On this slide, I'm breaking apart what this little formula is, okay? First of all, we're going from A to B, okay? We're going to find an area between A and B, which we were doing last, right? And we're going to partition A to B. What's a partition? Okay, we're going to separate it into pieces that added together equal the whole thing. Okay? And our partition, we're going to break up into all of these little sub-intervals from A to B. Okay? So we're going to start at A, and then we're going to move to x1, and then x2, and then x3, all the way up to B. Okay? So we're going to partition into all these little pieces to make our rectangles. Okay? The width of each subinterval is going to be delta xi. So what's the difference from one to the other? Okay? So, okay, how far apart are these?
Delta xi.
Okay? So that means. Now, C is any point in the subinterval. Okay? And here we have this. Now I know that this is Ci and my other one is Xk. Alright? Xk I'm actually going to, it's going to have a special meaning. Okay? So basically what we're doing, we're taking the width of all of these really, really tiny rectangles, and we're going to multiply it times the height of each particular rectangle. Alright? And we're going to add them up from 1 to n. Alright? So we have n rectangles with this as their width times whatever their height is. We're going to add them all up together.
So the F of CI is the height.
Yes. So we have the summation of our rectangular partitions. If we take the limit as n goes to infinity, we're finding the exact area under the curve. Right now we have n rectangles that we're adding together. As we take those n rectangles and we make them go to infinity, we are adding up an infinite number of rectangles, which gives us our exact area. Okay? Now we can do this with right endpoints or left endpoints. Okay? What we're going to do is we're just going to stick to right endpoint approximations for our Riemann sums because they are easier to write. Are you okay with taking the easier of the two? No, I'm saying you want to do the hard one? Okay. So, if we want the area under the curve using right endpoints, okay? First of all, on the right side, this is my definite integral. From A to B, I want the area, okay? F of x dx. All right, when we integrate, we are finding the area under the curve, is what that is saying. All right? Now, since we are using right endpoint approximations, let's visualize what our right endpoints look like. Okay, where do we start, so on and so forth. So if I have this picture from A to B. If I'm using, we'll just put a few rectangles in here. Obviously, there's going to be more than this thing, right? If I'm using right endpoint, what does this rectangle look like? Okay. We use the right side, correct? Maybe I should draw a curve that has a little bit more definition than that. I'll draw a really steep one. There we go. Steep line. So we're going to use the right side, correct?
Right. Yeah, that's really good.
Okay. This delta x, this is standing for the width of our rectangles. How do we find the width of our rectangles?
B use A again.
You agree with Brady? Okay. Now, this is going to be the height of each of our rectangles if we're talking about a right endpoint approximation. Okay. Do we start with, okay, how high is this first rectangle? Does it have height A?
No.
It does not. Okay. It has height, whatever this is on the right, correct? So, how far apart is A from this guy? Delta x, because that's the width of our rectangle, right? So x of k, we're going to write as this. First of all, we have to start with A. Second of all, we're going to add how far away we are from A. So our first rectangle is going to be delta x away from A. Our second rectangle is going to be 1, 2 widths away from A. Our third rectangle is going to be 1, 2, 3 widths away from A. That's why we have the k times the width. Whatever number of rectangle we are on, that's how many widths we are from A. Does everybody see that? Okay, does anybody need me to explain that again? Okay. So, we plug this value into our function to get the height at each rectangle. Here is the width of each rectangle. And by taking the limit towards infinity, okay, we find the exact area. Okay. Do we know how to take the limits of a Riemann sum?
No.
Okay. No, but do we have shortcuts for a Riemann sum?
That's the probable.
It's a yes or no question. Do we have shortcuts?
Yes.
Yes, we do. Okay. So we're going to talk about the shortcuts here in a little bit. The first thing I want to talk about are some properties we have with a definite integral. Okay. When we talked about integrals before Christmas break, we did not have this A or B right here. Those are called indefinite integrals. We just found the antiderivative. Okay. Now we have numbers here. So let's talk about these properties. First of all, if we take the integral from A to A, B to B, 5 to 5, 100 to 100, what's the area under the curve?
0.
Okay, there is no area if we're not going anywhere. So if you have the same limits of integration, okay, these numbers right here are called limits of integration, then it is 0. The area is 0. There is nothing there because we don't have an interval. Okay. If you have the integral from B to A, when you flip-flop the limits of integration, it becomes the negative of what the first one was. So the integral from B to A is the opposite of the integral A to B. They have the same area, it's just opposite. In calculus, it is okay to have negative area. Only in calculus. You don't like that? Next property, if we have the integral from A to C of a function, plus the integral of C to B of the same function, notice how the upper limit of integration and the lower limit of integration match. We can combine that to one integral from A to B. Okay. Now these next two properties we've kind of already talked about informally when we did our antiderivatives. If we have two functions added or subtracted inside of our integral, we can separate it out into two different integrals. Just make sure this time you keep the limits of integration the same. And then the last one, if there's a constant inside, you cancel it out in front of the integral. That one, again, we have informally discussed. So these are properties that you're going to need to know for well, you're going to need to know them for the rest of the year, but this week we're going to use them quite a bit. Okay. I promised we would talk about our shortcuts for our summations. Okay. First of all, we are dealing with the limit of a summation. If I can take this summation and write it as something that's not a summation using our shortcut, we can actually evaluate the limit of it. All right? So let's look at some shortcuts. Go ahead and write this one down. Remember how I was picky about your variables matching with your summation? Here is why it's important. We're dealing with n's and k's, and there is a big difference. Okay, so we have the summation of from k equals 1 to n of 1. Okay, times 1 over n, and we're taking that limit towards infinity. Well, can we rewrite the summation from 1 to n of 1? What can we rewrite that as? We can rewrite it as n. We have a constant that we're adding up n different times. Okay. 1 over n times n is? What's the limit as n approaches infinity of 1? 1. Next one. Okay, so we need to write we need to rewrite the summation from 1 to n of k. How do we write that? What's the summation from 1 to n of k? We're adding up k n times.
N to the k. N squared.
N times.
X.
Okay, so we're plugging in 1. Sorry, I said that wrong, didn't I? We're plugging in 1, and then we're adding it to when we plug in 2, and then we're adding it to when we plug in 3, and then all the way to n. I'm sorry, I said that incorrectly. Okay, what's our shortcut if we...
N times n plus 1 over 2.
That's what I was looking for. I apologize. Are we all on the same page now? No? Yes. That's our shortcut formula for k to the first power, right? Okay. Now, we have to remember back to limits. We have the limit as n approaches infinity of n squared plus n over 2n squared. When we look at at limits towards infinity, and we're talking about a rational function, what are we looking at? Our horizontal asymptote. Where is our horizontal asymptote?
0.
In this case, it's 1/2 because we have n squared over n squared. The degrees are the same, so we look at the coefficient. So our limit is 1/2. This is a nice little reminder, right? Next one. What?
Oops.
Should I just, take this off for now? Okay. So, we have the limit as n approaches infinity. 1 over n cubed stays because we're plugging in values k. Alright, if we have k squared summed up from 1 to n.
N times 2n plus 1 times
n
Over 6.
times n plus 1 times 2n plus 1 all over 6. Okay? Now, we don't really have to multiply this whole thing out because we have a pretty good understanding of rational functions. What is the degree of the numerator?
All the way to 3.
The degree is 3. We're going to have n cubed upstairs, won't we? Downstairs,
3.
our degree is 3. So we need to look at the coefficients. What is the coefficient of n cubed upstairs?
2.
Downstairs?
6.
6. So what's our limit? 1/3.
One.
Yeah.
Nolan thinks it's 1/4. We shall see.
Dun, dun, dun.
Okay. So we're going to have the limit as n approaches infinity of 1 over n to the 4th. What's the summation shortcut from k equals 1 to n of k cubed? Okay. I have n times n plus 1, and then it's squared. So what's the degree up top?
4.
4. The degree in the bottom?
4.
What's the coefficient upstairs for n to the 4th? 1. Please wait for my question. What is the degree down, or what is the coefficient of n to the 4th downstairs?
4.
So our limit is 1/4.
No one rocks.
Great job. Okay.
This is actually only 1/5.
Now, let's actually use these all together with finding the area under the curve.
Oh boy.
Okay. So first of all, you're going to need to be able to look at a picture and actually tell me what the integral is. Okay? So, we're looking at the area under the curve from where to where? 0 to 5. Which means this is the integral from 0 to 5 of our function, in this case it's x squared, dx. Okay. So, now we need our delta x and our x sub k. So our delta x, how do we find it?
5 over 0 minus
B minus a
yeah.
over n. So our delta x is 5 over n. That's how wide each of our rectangles are, 5 over n. Now we need x sub k. Remember, we're taking the right-handed endpoints for our rectangles. So we're going to start with a, which is 0, and we're going to add the width over and over. So our x of k is just 5 over n times k. So our integral from 0 to 5 of x squared dx is the limit as the number of rectangles approaches infinity of the summation when k equals 1 to n of our f of x sub k times delta x. Okay? So we have the limit as n approaches infinity. When we plug our x of k into our function, what is that?
25 squared.
We'll put 5 over n times k squared. Right? We'll do that for now. And then what is our delta x? 5 over n. Ooh, I forgot my summation. I'm sorry. There you go. Okay, so what are we summing up? What does that simplify to? 5 squared times 5.
125 over n cubed
Times
a squared.
squared. Okay. Now 125 over n cubed technically is a, well, okay. For my summation, I'm plugging in values for k. So the 125 over n cubed, am I plugging in, it's technically a constant, right? I'm not plugging into n. I'm plugging into k. So we have the limit as n approaches infinity. We have 125 over n cubed. What about, what's our shortcut from k is 1 to n of k squared?
It would be the n times n plus, no, it's going to be n times n plus 1 raised plus over 6. Plus 1 over 6.
Wow. Okay.
14.
Good.
Can you go back to okay. So I get but when it says x of k and it's
Uh-huh. No, this is the function evaluated at x of k, so we're plugging x of k into x squared. This is the function notation, because f of x equals x squared. This means plug, okay. If you want to write it as x of k squared, if you want to, or x of k squared plus 5, or whatever the function is, that's fine, if that helps you. Okay? So now let's talk about this limit. Do you agree we have n cubed upstairs? And we have n cubed downstairs. So if we're looking at the limit towards infinity, we're looking at the horizontal asymptote, which is going to be the ratio of the coefficients, which is
50 over 6.
125 over 3.
Yep.
That is the exact area using our right hand endpoint rectangles.
So that is exact.
That is exact. We took the sum of an infinite number of rectangles
Wow.
that are infinitely small. Okay.
Where's that? Sine.
Is everyone okay with what we just did? We're going to do another one. Okay? Okay. Is there? You okay? Infinitely many rectangles. You guys don't really like that? No?
I just don't like running the limit and then it goes to infinity and the summation over and over again.
You'll get over it. All right. We're going to do this one now. First of all, let's express what the integral is. We have the integral from -2 to 2 of our function dx. Putting 4 minus x squared in parentheses is very important. Make sure you have your dx. That's what tells you what you're integrating with respect to. Okay? Technically, this dx, that's the width of all of your infinitely many rectangles. All right. Now we need to write our summation. So delta x. How do we find it? B minus a over n. X sub k. We're doing right-handed endpoints.
-2.
So a plus
plus k times 4n.
for our Riemann sum, what are we actually going to have to do with x of k?
Plug it back into the evaluated factors.
Okay? Here, I'll write our summation over here. So the integral from negative 2 to 2 of 4 minus x squared dx is going to be the limits as n approaches infinity, the summation k equals 1 to n of our function evaluated at x of k that tells us how high each of our rectangles is times delta x. So what I need is our function evaluated at x of k. Alright? This is going to take a little bit of algebra, isn't it?
Just a little bit.
Because we're taking negative 2 plus 4 over nk and we're plugging it into 4 minus x squared. So we have 4 minus negative 2 plus 4 over nk quantity squared.
Oh boy.
So we plug it into the equation as if it were x.
So we have 4 minus the quantity. When we square this,
We get 4 squared, or 4
negative 2 times negative 2 is 4.
plus 16 k there.
Okay. Now if we take
Minus
because we're foiling this, right? The outside and the inside, since we're squaring a binomial, get us the same thing. So we have 2 times a times b, which is 8 over nk. And I put the negative out in front. Is that okay? And then b squared is what?
16 k squared.
So f of x of k is 4 minus 4 goes away, right? And then we have what? That?
What is
The second one should, right?
No,
No,
first
no,
one.
first.
Isn't this minus?
It's a second.
Minus. So that turns to plus and then alright? Okay.
What if it's 4 minus 4?
The negative distributes all the way through. So we have the limit as n approaches infinity of the summation k equals 1 to n of 16 over nk minus 16 over n squared k squared times our width of each, which is 4 over n. Okay.
Okay.
So let's go ahead and break this into 2 different summations. Sound good? We have the summation of k equals 1 to n. When I take 4 over n times 16 over nk, we get 64 over n squared k, right? Minus 64 over n cubed k squared. So we have 64 over n squared what's the shortcut for when we're summing up from 1 to n of k? N times n plus 1 over 2. Okay. Minus, we have 64 over n cubed, and we're summing up k squared.
N times n plus 1 times 2n plus 1 is 6.
Okay. So this first limit we're going to evaluate, we have a rational function where the degree on the numerator and denominator is both 2, correct? So we look at the horizontal asymptote, which is what the ratio of our coefficients is. In this case, that would be. What's going to be the ratio of our coefficients?
64.
32. Minus. Here I have a third degree over a third degree, so we get to look at the coefficients again. We see a pattern, don't we? Okay, what's the coefficient up here? 64 times 2, right? Over 6 gives us
32.
what? Oh, you already did this math? 32 thirds?
Yeah.
Okay. 10 and 2 thirds. There's the exact area. What, Chrissy? Okay. This is nice because we're reviewing our shortcuts from last week and we're reviewing limits from chapter 1.
Which I think.
Okay, every single limit that we've done has been a rational expression towards infinity where the ratio of the coefficients.
Go on.
Okay. Have you noticed that?
Yes, is that the case with all? Will that be the case?
It could be.
That doesn't sound very positive.
Or what if there's
Okay, this is the last thing I want to look at because you'll have a couple like these on your homework. Now look, I've given you an integral and what it equals. Okay? We're not doing Riemann sums in this problem.
Yay.
Alright? So I have the integral from 0 to 5 of function f is 10, and the integral from 5 to 7 of function f is 3. How do we get the integral from 0 to 7? We add them together. From 0 to 5 plus 5 to 7, okay, is the same. So, what is our integral? 13. Okay.
negative 10?
The integral from 5 to 0
Negative.
is the opposite of the integral from 0 to 5. The integral from 5 to 5.
0.
The integral from 0 to 5 of 3 times our function. Okay, because we can take this 3 out and multiply it times our integral, which means we have 3 times 10. That's there you go.